Hi and welcome. This is an AQA Physics Paper 2 live stream, but it is useful for all exam boards, so don't just jump the gun if you're thinking that, okay, that's not for me, that's AQA, because all I'm going to do today will be useful for all exam boards. Some of the questions might not be about to come up in your one, but still the way we go through and the way we solve them will be useful. And if you're, for example, OCR, then I've got loads of OCR feeds and the OCR Paper 2 stuff in the description. That's OCR Gateway. So over those two specifications, we should pretty much cover all the content that's going to come up in your exam tomorrow. This is your last little bit now, okay? After this, you can enjoy your summer holidays, and this is going to be an amazing long summer, and I really want you to relax and enjoy your summer holiday. Everybody does, okay? We know it's been a stressful period, but one last little push, one last morning, and you can really start to relax. For most of you, although I know some of you are going to have some of you are going to have an exam or two next week, okay? So I'm going to go through about 6 of the hardest AQA GCSE Physics questions from Paper 2. In between each one, I'm going to stop and I'm going to have a little look at the chat, okay? And by doing that, then you'll be able to ask me questions if something wasn't clear in the way I explained how you answer the question, or you've got something that you want me to quickly whiz through or something like that, then you can ask then. Okay, so basically we're going to jump straight into well, I'll have a little look at the chat first, okay, and then we're going to jump straight into the first question. Alright. Okay, so I've already had a question that I just wanted to address before we started then. Is it okay if when describing wavelengths I use the word emit instead of reflect? Well, no, if you mean reflect, then we ought to use the word reflect. So emit means to give out, and reflect means that it's hit a surface and it's come back with an angle equal to the angle that it hit that surface. Okay. I'm really glad Mr. Denver here is a A-level student who's just finished his A-level physics, and so is here to probably gloat over you guys. So maybe Mr. Denver, if you want to watch, then well, don't just slag off biology, because you know I'm not a biologist, but I'm glad yours went okay today. Maybe you can give some good advice to, relax about this paper that's coming up. Go in there and do your best. Right, so we're going to jump into this AQA paper. Okay, thanks, I'm glad to have helped, guys. Okay, I'm glad, Marion, that it went okay for you. So now this is GCSE tomorrow, okay, and then they're done their physics and they can start to relax. And in fact, for most of the GCSE students, that'll be done now. Okay, okay, so I'm going to come back to the flux density and left-hand rule later on. Okay, so I'm going to jump into the questions just now. Let's do that. So this first question, and straight away they've given you a huge context that you had no idea was coming up, and the context is CERN, okay, which is the kind of Centre European for Research Nuclear. It's the nuclear physics lab where they're colliding large hadrons, okay, and making things like that. But actually the question doesn't really actually ask you anything about CERN. So this is just a context, right? Now try not to be put off by the context, and what we want to avoid is all the Hitler reacts to AQA Physics Paper 2 tomorrow, okay? We don't want to see all those memes. We want to know that we've been able to struggle our way through, not be put off by the contest, but just read the question, suggest why most other scientists thought the experimental results were unbelievable. So it's about these neutrinos that they detected that appeared to have travelled faster than the speed of light. And it tells you these results challenged the physics theory that nothing can travel faster than the speed of light. So really this is not a question about particle physics, it's not a question about CERN. It's a question which is asking you, do you know why it's difficult for scientists to accept new results that don't agree with accepted theories? So the answer that I've kind of put down was that lots of other evidence, that's the point, isn't there? Lots of evidence support this theory that nothing can travel faster than light. So they gave you a few other options. You could have had the theory supported by results from other experiments. That's basically what I've said. Couldn't have believed the theory could be wrong, or the theory is the basis of other ideas. Okay, so there's loads of ideas that maybe were brought about by Einstein and people like that actually we can't just scrap them. So what do they do then? Well, they publish their results. And now you've got to suggest 2 reasons why they decided to publish their results. And again, you're not thinking, oh, I don't know anything about CERN, I didn't know CERN was going to come up. This is just, why do scientists publish their results? Well, it's to allow a process of peer review. And you could have said something like, to check the data, to repeat the experiment and check if their findings were reproducible, which is another point you could have made, okay? Other scientists can develop the theory or develop the experiments or develop the explanations. That is why scientists publish results. So this is not really a question about CERN. It is a question about why do we change our theories when we get new evidence, or struggle to change them when we've got spurious evidence and evidence that we don't necessarily trust. And then it's about why do we publish results. And then look guys, this is just a good old speed is distance over time. So velocity is displacement over time question, and it's just asking you to calculate the time. It's giving you some really big numbers, but look, there's a distance and there's a speed, and this is, you know, it's not even hidden in the data because they've actually told you it all twice. So you can just rearrange for time. Time is distance over speed, and then input the numbers and do this into the calculator. You get all this onto the calculator. Okay, now if I've done that, I've rearranged and I've put my numbers in and I've got this long number, I've only got 2 out of the 3 possible marks, because look back, give your answer in standard form. So you must then convert to standard form, which is about having a number between 1 and 10, and then the 10 to the power of something. Thank you very much, PG, for the super chat. Okay. So I'll just say that when you do this type of thing, make sure you count zeros into the calculator, and when you're checking through your work, count zeros again, double check yourself, because you will make mistakes. Now they haven't given you these values in standard form, but you can do times 10 to the X button on your calculator, and I hope you can all do that. So that will come up later, and I'll show you how to make sure to use that times 10 to the X button on your calculator for very large numbers and very small numbers, because do you know what, that needs to be done. Alright, the next one, again, it tells you about scientists found the unexpected results were caused by a timing error. So they reviewed it and they realised there was an error, something they did wrong. The error meant the time recorded was always 60 nanoseconds less than the average time. Which one of the following is the same as 60 nanoseconds? So this is just, do you know your prefixes? So a milli is times 10 to the minus 3, a micro is times 10 to the minus 6, and a nano is times 10 to the minus 9. So that was just the 60 times 10 to the minus 9 seconds, 60 nanoseconds. What name do we give to this? Well, this is a zero error or a systematic error. And actually I think zero error is better than a systematic error, because the systematic error is like the group of errors. It can either be systematic errors or random errors, and specifically this is a zero error. When it should say 0, it should read 0, and it didn't. It would read 60 nanoseconds, right? So suggest what the scientists, or it would be minus 60 nanoseconds at 0. Suggest what the scientists should do to calculate an accurate value for the speed of a neutrino. All they need to do then was get rid of that systematic error, get rid of that zero error by adding 60 nanoseconds to each reading. You could have said something like, or recalibrate and set to 0 again. So I just want to say, before I have a little look in the chat and see if there's any questions, I just want to say there are 2 main groups of errors: random errors and systematic errors. And random errors are the ones that we can get rid of, or not get rid of, but we can limit the effect of by doing repeats, spotting anomalies and eliminating them, and calculating averages. Systematic errors are where we have to actually change what we're doing. There's a way in the analysis that we can actually change what we're doing to ensure that we're accurate. Right, okay, so that is the first question. Going to come back on to this next question in just a moment, but let's just have a quick look at the chat. Take myself a little break from thinking, and we'll see questions that I can answer now. Okay, lots of people talking about last exam. That's really good news as well. Radiation and reflection, absorption, scattering, and that. Could talk about that. Parallelogram of forces. So just remember, when you're doing scale drawings of forces, always do them top to tail. So the top of the arrow meets the tail of the arrow, and if you do that, and you do that to scale with a protractor, you're going to get it right. If the parallelogram closes, it's in equilibrium. If it doesn't, then it's not in equilibrium. Radiation, reflections, absorption and scattering. Now I meant to say that at the start. Somebody asked, is it okay if when describing the word I use emit instead of reflect? So reflection and refraction, okay, and diffraction are 3 behaviours of waves. Okay, so refraction is when a wave goes into a medium where it changes speed. If it slows down, then it refracts towards a normal. So you have to be able to draw, sketch or recognise when you've got a refraction or reflection. So here we go, wave comes in. If it's going from like lower density, so like air, to glass, then it refracts towards a normal. Okay, and this is the line, the normal at 90 degrees to the surface. This is the angle of incidence, this is the angle of refraction. I don't know if that kind of does everything. Absorption and scattering. So absorption is if it didn't do this, if it just, the energy was taken in by the material. So opaque things tend to absorb light, or they tend to scatter light. So if I have a plane mirror, and what we do with a plane mirror is a really smooth surface, maybe I should have used a ruler, is shade the back to show that the light can't go through it, we'd get reflection. Okay, and the law of reflection is that the angle of incidence is equal to the angle of reflection. Okay, basically, and we always measure, remember, we always measure between a ray and a normal, never between the surface and a normal, right? Now if something is a, you know, if we were to zoom in on it, it's not a very smooth surface, then when the light hits these, it scatters off in all different directions. Yeah, I hope that makes sense. And that means we don't get a uniform kind of image that we do when we have something that was perfectly smooth. Okay, it's nice to see Mr. Denver giving a good a bit of advice. You should definitely relax before you go into the exam. I'm just going to do 1 hour here, and then you're all going to go and relax. Okay. Tim Bob says, I got an A star on this, it can't be that hard, but of course you all know that they've made these GCSEs that bit harder, and the way they made them harder is they brought down some stuff from A level basically. Magnets and stuff, defo, alternating dynamo graphs. Okay, I can do alternating dynamo graphs sort of straight away, just give me a moment. So alternators produce AC, so voltage and time. Okay, so basically this is just a changing voltage, and a dynamo. Okay, the voltage is always positive, so it's still increasing and decreasing though as the magnet turns within the thing, but they're always positive. Okay, I hope that makes sense. Now this is direct current because it's always positive, and the definition of AC is varying positive to negative. Okay, so let's just leave that there for a little while, and let's go back into our next question, and then I'll come back to the chat. Okay, so what's the difference, first of all, between distance and displacement? Okay, well, you didn't even need to understand anything of this stuff about the train. What's the difference in distance and displacement? So this is just define, essentially, the difference between distance and displacement. Distance is scalar, displacement is vector. Actually, that was enough to get you the 1 mark, but you could have also said distance has only size, displacement has size and direction. They might ask you to define a scalar and a vector, so I thought I'd write that all in for you, okay? Scalar, only size, vector, size and direction. Distance is the scalar, displacement is the vector. Determine the displacement of the train travelling from A to B and show how you obtain the answer. So that's using the thing, and they've told you this is a scale drawing. They've told you 1 centimetre represents 5 kilometres, so I hope you get the idea. You just have to measure the straight line as the crow flies, which would be the displacement. And you measure that with a ruler. You get 7.5 centimetres. So each centimetre is worth 5, so you get 37.5 kilometres. Now you only got 1 mark so far because it's asked you for displacement. So you also need to indicate the direction, right? So actually the way you would do this is you would make a bearing from north using a protractor. Okay, now that's pretty tricky that they've given you north there, so they have given you a little bit of leeway if this line isn't perfectly parallel with this north here, but you use a protractor to measure that angle essentially. And bearings always have 3 digits, so 062. Now if you're expected to use a protractor at any point in the exam, it will say on the front you need a protractor for this exam, and if you don't have one, okay, because you're not prepared for that exam, make sure you do take one with you. If you don't have one, then put your hand up and ask for one because you're due one. Alright, so I'll leave that at that. So there are places on the journey where the train accelerates without changing speed. Explain how this can happen. Well, velocity can change if the train changes direction. Remember we said that velocity, or rather, we haven't said about velocity, have we? We talked about displacement. So velocity is displacement over time. So if the changes direction, then it's changed the vector displacement. So therefore, velocity has changed, first mark. And acceleration is a rate of change of velocity, not rate of change of speed. And I've put the little equation there. A is delta v over t. Acceleration is a change in velocity over time, gives you the acceleration. So if you learn the equations really, really well, which I'm sure you have, then you can ensure that you can answer the questions with the equations. Right, now we've got a graph, and you always check what type of graph have I got before you do anything with graphs. We've got a velocity time graph, so we need to think the gradient is the acceleration, the area underneath it is the distance. Okay, so here we go. Estimate the distance travelled by the train along the section of the journey shown in figure 15. So that's the whole figure, right? The whole thing. To gain full marks, you must show your work, take your answer right. Well, basically, I've said to the examiner then, I know distance is the area underneath a velocity time graph. And if you do that, actually, it's probably going to be worth a mark, okay? Or actually showing that that's what you are doing. So we worked out what one small square is worth. Okay, if there's the area, then each small square is 5 times 100. So each small square is worth 500 meters. And then from that, we just counted the squares, and counting the squares is a difficult technique, and you can actually section the whole graph into triangles and rectangles. When you're counting squares, you need to first of all count all the full squares, and then look at some kind of half squares that you can make into kind of one full square. So count all these: 5, 16, yeah, and you'd add all these up, and you'd have somewhere between 15 and 18 squares. Okay, that was the estimate they're happy with. So 17 is what I got when I did this earlier, and 17 times 500 gives you 8,500 meters, which is 17 times 500 is your next mark, and the final answer is your third mark. Okay, glad this is really helpful, Charlie. I'm just going to have another little look at the chat, so why not? Okay. So gears, yeah, Florence, I can go over gears really quickly. Gears are very, very simple. They are force multipliers, and essentially you have 2 or more cogs with different diameters. Okay, so let's get my book again. And the force is multiplied in the ratio of the diameters. So if this is a diameter of 1, this has a diameter of 2, then if I put a force in here, F, then the force I get out of this one is 2F, twice the force. Now similarly, if that was driven the other way, then if I put F in here, I'd get half F out here. So the force is just multiplied in the ratio of the diameters. Now it might be they give you teeth. Okay, now gears have teeth which make them interlock, right? I'm not going to draw them all, but I hope you get the idea. And actually, because the circumference of a circle is pi times d, then the number of gears, if they're evenly spaced, is proportional to the diameter anyway. So also the number of teeth, the ratio of the number of teeth. So if I draw 2 gears and I have 20 teeth and 40 teeth, then I've got a ratio of 1 to 2 again, so I've multiplied the forces again. The only other thing they ask you is about which direction is it turning. If I'm turning this one clockwise, then this one's going to have to turn anti-clockwise. And they can sometimes give you more than just 2, so they might add a second one on here. So this one's turning this way, so this one is going to turn this way. Okay? Is that right? That's wrong. So this one's going to turn clockwise again. Now, this one is going to turn clockwise. Now, when you do this, you don't need to worry about the second gear for the forces. So you just look at the diameter. If this had a diameter of, let's say, 3, then this force out here, which is now the same direction, would be 3F. Okay? I hope that makes sense. Any other bits? I'm not going to do one for Combined Science tonight. This is my one live feed for tonight. Magnet stuff. What exactly do we want in magnets? It's quite a big topic. Is it just the simple opposites attract stuff? Is it about the shape of the field? Is it about the currents? Okay, you tell me. Okay, loads of people talking about AQ at the A level earlier on. and also talking about the 500k subs party. Well, it's not going to be 500. I had a live video where I said we're going to play Hunt the Teacher for we're going to play Hunt the Teacher for I said 500k subs, but I meant 500,000 views. So 500k views I think is pretty impressive still. So I'm going to do a little celebration of that after exams, so stick around for that. But yeah, I think that's funny. Maybe one day we'll be celebrating the 500k subs. And somebody says, guys, it's my birthday tomorrow. So yeah, it is my birthday tomorrow. And you don't need to donate, but thanks for the thought. Maybe in the future when you get that amount of money, or maybe if you know your family is particularly well off and you want to, I do have a Patreon account as well that you can find, patreon.com GorillaPhysics, and you can be part of my community there and help me kind of develop my channel in the future. But I'm really glad. How else I'll be learning this wonderful subject. It's really good, PG. Alright, okay, so awesome stuff. I'm going to ask you, whilst I'm doing the next question, if you wanted to answer this question, what are you guys doing for A-level, you GCSE students, okay? I know what a lot of the A-level students are doing for their degrees. That was really interesting. So what are you picking for your A-level? What are you hoping to do next year A-level? Let's go ahead and do the next question. Okay. So this one is about stopping distances, basically, and stopping distance, you should know, is the sum of the thinking distance and braking distance. So what's meant by the braking distance? That's the distance travelled whilst the brakes are applied. Now here, this sounds really silly, but here's the mistake that people make. They go ahead, the braking distance, and they then write the time travelled or something like that. Okay, so make sure when we're talking about braking distances, it's dissimilar from the braking time, for example, right? So make sure that you get that the right way around. Then explain why the stopping distance of the car increases if the driver is very tired. So if the driver is very tired, the reaction time increases, so therefore the thinking distance increases. So they've asked you to explain why the stopping distance increases, so reaction time is only half of the argument. Reaction time increases, so therefore the thinking distance increases. Okay, so here we go. Student writes the following, and I hope you know this little fish symbol is proportional to. It means if I double this, I double this, if I double this, I double this. So let's have a look at that. Thinking distance is proportional to speed. If you double thinking distance, you double speed. Yeah, that is the case, that is true. Braking distance is not proportional though to speed. Alright, so this is a mistake. You have to explain whether the student is correct. So first of all, your first mark is, yeah, it is correct that thinking distance is proportional to speed, but braking distance is proportional to speed squared. Okay, that's your first mark. Or actually, you could get a mark here, one of the marks, just by saying they're not proportional, part right, part wrong. Now, if you look at the data, and this is what you should do, if you get given data, make sure that you do use it, then you can see that if you double the speed from 10 to 20, then you quadruple the braking distance. Okay, you double the thinking distance, that's okay, that was the first bit, but you quadruple the braking distance. And this is because under braking, you are dissipating kinetic energy. So I've done that with some data. I've said speed doubles from 10 to 20, braking distance quadruples from 6 to 24. Okay, so here we go. Why is it important the sled is pulled at constant speed? So this is a whole thing about an experiment that you can do to investigate friction. Okay, they're looking at the friction constant. But looking at this, why is it important that the sled is pulled at constant speed? Okay, if the sled accelerates, it'll be difficult to control. No, that's not really what we're on about here. If the sled accelerates, the value for the constant of friction will be wrong. Okay, yeah, that is the answer. If the sled accelerates, the normal contact force will change. Now, the normal contact force is a force like upwards at right angles, so it's not about that, right? So what you need to do here is you need to think about Newton 1. And basically in this bump, they've talked about you're measuring the friction by pulling this at a constant speed. Now at a constant speed, according to Newton's first law, the forces are balanced. So if you pull it at a constant speed, you know the force you're pulling with is equal to the friction. So if you just have a Newton meter or something here, yeah, then it'd be measuring the force out here, and you'd know that that would be the same as the friction. Now, this wouldn't actually be the same as the friction, as we're going to talk about in the next one. I've told you this is the correct situation. So this force would be the same as friction. Now, why is that? Is what the next question is going to ask us, right? If the sled is pulled at an angle to the surface, the value for the constant of friction would not be appropriate. It wouldn't be valid, right? Friction acts in the horizontal plane. So if pulled at an angle, only a component of force measured is horizontal. So we're trying to measure friction, which is, in this case, in the horizontal plane. We need to measure the force in the horizontal plane, not at an angle. Right? That means that this can be split apart into two forces, a vertical component, y component, and an x component. And we're not interested in the y component, we're interested in the x. The force measured will be the hypotenuse of a right angled triangle. So we need to say that somehow. This means there's lift, or this means there's a vertical component reducing the friction, making the result not valid. Okay. And then the next one says, by measuring the length of the skid marks, an accident investigator determines the distance of the car travelled was 22 metres. The investigator used a sled to determine the friction. The investigator calculated the car decelerated at 7.2 metres per second squared. Calculate the speed of the car just before the brakes were applied and give your answer to two significant figures. So these are the two command words. It's also told you there's an equation on the physics equation sheet, which is this one. V squared equals u squared plus 2as, or they sometimes write that slightly differently, but that's the equation. And it doesn't seem at first like we know everything we need to know. We know a distance, we know s, okay, that's this one here. We know an acceleration, we know 7.2 meters per second squared. We don't know, obviously, the speed that we're trying to work out, the initial speed. That was what we want to work out. They haven't told us the final speed, or have they? They've told us that it's come to a stop somewhere in this, or it's implied it's come to a stop. So V equals 0. So the extra information was the stuff that they didn't tell us, but we kind of knew anyway. So the way to do these is often just to plug in all the numbers that you know, then simplify. So I can move my u squared over here to minus u squared, and I can multiply all this together. Incidentally, we should really use minus 7.2 because it's slowing down. And that cancels though at this step here. So minus u squared equals 316.8. So u is the root of 316.8, and you get all this on your calculator, and so far you've only got, for all that, you only got 2 marks. Have you spotted where the third mark is? So check back through the question once you've done your working out. Have you done everything they've told you to do? And if you've underlined only the bits they've told you to do, you can check that more readily. They've told you to give your answer to 2 sig figs. So rounding to 2 sig figs is the last mark, and there's quite a lot of that on the AQA physics papers. Right, here's the next one. It's about atmospheric pressure. We've got 3 more to go, but we'll have a quick look just into the chat, and whilst you're doing that, you can enjoy me looking at this gorilla that I found was covered in butterflies and the cake somebody made in my class. Okay, so I'm glad people are saying this is helpful. I'm glad people are wishing me a happy birthday. That's nice. It'll be a good day tomorrow. We'll have finished exams. It'll be good. Left and right hand rule. Okay, so right hand rule is only for EM induction. Alright, so we don't really use that at GCSE. I don't know if that is, but the letters are still the same. Okay, still a force, still a field, it's still a current. Okay, but in GCSE we do the motor effect, and we only really do the left hand rule. Okay, I hope it looks like that's my left hand. It's not mirrored on there, right? So the force, the field, and the current. Okay, now the purpose of this is just to be able to orientate this in space to work out the direction of a force or of a current that caused the force, right? Or a field, indeed. And just remember that the drawings they make, the 3D drawings, are never really very clear. But there's only kind of 3 dimensions. There's left or right on the page, there's up or down the page, or there's into or out of the page. Right, so they're your kind of 3 directions, and you need to just decide each direction to work out a third direction. It's a bit like an equation, right? It's a bit like you need to measure, you've got 2 things and you can work out a third. You've got 2 directions and you can work out a third. So people doing maths, further maths, and of course physics, top stuff, okay, maybe going to engineering in the future, maybe. A-level English, Lit, French and politics, okay, good luck with those. That's a really interesting mix. H123. James says physics, chemistry, maths and further maths. That's a great mix. Okay, maybe natural sciences for you, James. And who else? Nikhil. A-level maths, business and chemistry. That's a really interesting mix, actually. Okay, some good challenge in there. Split ring commutators in motors versus DC in current production. So a split ring commutator is used for anything that's DC, okay, as opposed to a slip ring. So just remember that slip rings on the AC generator You don't really have an AC motor, although you could work as a motor, but it'd have a fixed kind of speed. The split rings, okay, mean that every half turn, a different side of the coil connects with a different side of the circuit, and that means you get constantly positive out in a dynamo, or you can run a motor on direct current. Because every single half turn, the current in the coil is switching, meaning the force is always the same on one side. The force is always the same on a certain side of the motor, and it always rotates in the right direction, either clockwise or anti-clockwise. It doesn't switch halfway between. Hope that makes sense. Right, okay, so let's move on then, please. We'll do the next question. Okay, so this next one just asks us to explain why atmospheric pressure decreases with increasing altitude. Now again, you could have done that without the graph. So this is not coming from the graph. We're going to use the graph a little bit later, but you could have actually explained why atmospheric pressure decreases with increasing altitude without the graph. Now, all we're really looking for in this is your idea that at higher altitudes there are fewer particles above the objects. So there's less weight pushing down on any surface. Okay, so either of those 2 points are actually good enough for the mark there. Okay, gas pressure is caused by particles colliding with surfaces. So whenever you're explaining gas pressure, I want you to talk about particles colliding with surfaces. And actually, if they collide more often, not more, but more often, or with more force, then you get a higher pressure. So in this case, we've got a lower force, so we've got a lower pressure. So here's what I've said next. Gas pressure is caused by particles colliding with surfaces. There are fewer particles colliding per second, lower frequency, and they collide with less force, so therefore lower pressure. So the next mark there is for lower frequency, less often. So really always explain gas pressure in terms of frequency of particle collisions and the force of them. Okay, it is the net force at right angles to a surface basically is still pressure is force over area. I'm going to use that in the next bit here. Now, these are really quite tricky, but again, tricky context, just think I'm trying to pick up some marks. This is a 5-mark calculation. Can you pick up some marks? Because if you just notice you've got a pressure and you've got an area, you can pick up marks by showing us that you can work out a force from this. But I'm going to take you through the reasoning of this one here. And again, give your answer to 2 significant figures. So if you can show us you can round to 2 significant figures correctly, then you're going to get a mark for that as well. So think about that. Firstly, you need to think about, well, we've got this, we're trying to work out the force, resultant force, acting on an aircraft window when the aircraft is flying an altitude of 12 kilometers. We've been told the pressure inside the cabin, but the resultant force, which is the clue here, okay, is equal to the pressure difference. So that's our first mark. We'll actually work out the pressure difference. So it's 70 kilopascals minus 20 kilopascals, because the 20 kilopascal is from the graph. So 12 kilometers, that's when we had to use the graph. You're thinking, oh, why did they give me that graph? And you can find 12 kilometers, you go up to the line with a ruler though, because you need to be half a small square accurate from graphs in GCSE, and you get 20 kilopascals. So the pressure difference that's going to cause that resultant force is 50 kilopascals, and that's what we need to use in our equation. Now, kilo, we need to make sure we get rid of that, and you can see I almost made this mistake. So get rid of kilo, 50 times 10 to the 3 pascals. That's the SI unit there. So now the next mark is for having the equation and rearranging it. Force is pressure times area. The next mark is for converting from kilopascals into pascals and from centimeters squared into meters squared. And that's one people really quite struggle with, because it's not a factor of 100, because it's centimeters, so it's not a factor of a million either. It's centimeters squared, so it's 100 times 100, so it's a factor of 10,000. See, I've actually done that right, luckily. So 50 times 10 to the 3 times 0.081, which is this in meters squared, gives me on my calculator 4,050. Okay, so sorry, I got a mark for all the conversions, remember that, and putting it in, and I got a mark for 4,050. Whereas the last mark, read back through, they've told us to give our answer to 2 significant figures. So let's make sure we do that. To 2 sig figs, 4,100, and that's your final mark. Okay, really tricky one, this one, and I know that the people who did this as a mock exam in my school, this was a lot of challenge, this one here. So let's just talk through this one here. It's quite a difficult one to get your head around. So the figure 18 shows the cross-section of one type of aircraft window. Now can you see it's curved on the inside, and it's also slanted inwards. This means this has a higher area than this does. Right? Now, why is that basically? Explain why the window's been designed. So I just have to go because there's somebody at the door. It was just a parcel, so I'll be back. Hi dudes, excuse me there. Okay, so essentially it's because of this higher pressure inside the cabin compared to outside. Because there's a higher pressure, we can reduce the overall force on the window by having a higher area. Okay, so because force is pressure times area. This means that the force inside can actually balance, because of the larger pressure we can reduce the force on the window because of that larger area. We're spreading it out over a larger area essentially. This means the force inside balances the force from outside. Tricky one. Okay, so this is number 11 and we've got 2 more to go. Is there any more chat there? Any more questions? Luke, I've just done parallelogram force just at the start, so I'm going to leave that one. Life cycle of stars, mainly the formation. So nebula, okay, which is a cloud of gas and dust, and you need really detailed things to this. So it comes together by gravity. Now you need to have that detail in there. If you don't get comes together by gravity, then you're probably going to have missed a mark. When they come together by gravity, its density increases and you get particles colliding more and they get friction and you get high temperature and pressure. And that's the detail you need to get in there. You get high friction, it gets hotter, so you get high temperature and pressure. When you get high temperature and pressure, then that's the right conditions for fusion to start. You need to probably say hydrogen and hydrogen fuse to make helium. And when you've got that, you've got what's called a protostar, which is a very small area but a very dense point, but fusion has started. Now fusion makes heat and makes therefore higher temperature and pressure. So fusion causes more fusion. And if you've got the right density, then you'll eventually start enough fusion to call it a main sequence star. A main sequence star has a balance between this radiation pressure outwards and the gravity holding it inwards, and that's why stars have these ball shapes, because there's this balance. Again, it's a Newton one of outwards force and inwards gravity. Outwards radiation pressure, and that's the name of the force, it's not necessarily a pressure. Outwards radiation pressure and inwards gravity. Get that word equilibrium maybe of forces in there somewhere. And then it's about different sizes of stars. The more massive stars have a shorter life cycle, shorter main sequence, and they expand into being red supergiants, and then they collapse down on themselves and bounce off this incredibly dense core, and in doing so they release lots more energy in an explosion. It's called a supernova. Now if that supernova is large enough, it will leave behind a black hole, which we just know is an incredibly dense radiator and absorber of electromagnetic radiation. We don't know anything else about it, but we know that it absorbs and emits all frequencies of electromagnetic radiation. Or it could be a neutron star, which means that all of the protons and neutrons of all those atoms have been condensed into such a small little point. They've actually kicked out all the protons. The protons have got so close they've repelled each other, so you've just got neutrons. And then the next one, the next option is if it was too small to do a supernova. Now if it's too small to do a supernova, then it's like our sun and it's going to go into a red giant instead of a supergiant, and it's going to puff, it's going to outgas all of the elements that it made, and it's going to leave behind a planetary nebula. And a planetary nebula is not a stellar nebula, so it won't give birth to any new stars. So you need a lot of detail for that. I've probably got a little bit excited, a little bit over the top there, but look for your revision guide and learn each stage of the life cycle of stars in a really kind of detailed fashion. Okay, I've done motor effect and sample select. Good on your H123. You've been around for a long time, and enjoy your combined science stuff. Okay, you might want to check back later after the stream, and you can skip through, see if there's anything else that was relevant to you. Right, let's go back to the questions. I've got 2 more questions, and I have a few more minutes. That's fine. Okay. So again, it's another question where we didn't even need to read the first little bit, but waves may be longitudinal or transverse. Describe the difference between longitudinal and transverse waves. So this is just, can you define really what they both are? Longitudinal waves have oscillations parallel to wave energy transfer. Mark. Transverse waves have oscillations perpendicular to wave energy transfer. Now a lot of people, when they revise this, they just revise longitudinal, parallel, transverse, perpendicular. 0 marks for that. So you have to memorize the detailed explanation. You have to relate the direction of the oscillation to the direction of the energy of the wave, the direction of the travel of the wave, if you like. So describe one piece of evidence that shows when a sound wave travels through the air, it's the wave and not the air itself that travels. Now I racked my brains, and the example they gave was if you bang a drum skin, it doesn't leave a vacuum around it. Right, fine, that is okay, that does make sense. But I was thinking that at a concert, like there's like smoke maybe in the air from smoke machines, and that doesn't move along with the waves. You don't see it like billowing with all the frequency of the waves, the sound waves that are coming, right? So that's what I put. But the problem is with this, a lot of people, they wrote something about like, oh, if you put a cork in the water and make a wave, the cork just bobs up and down and it doesn't travel along. Now, that wouldn't be appropriate for this because they've asked you about a sound wave, not about water. So make sure you're responding to the context given, otherwise your good physics that you no doubt will put down will not be credit worthy, will not be worth a mark in the exam. Right, so a coil of wire is positioned in the gap between north and south poles of a cylindrical magnet. Here we go. Explain how the loudspeaker converts current in an electrical circuit to a sound wave. An alternating, so I've just done this, okay. Before you start just launching into this, pause and plan. Okay, so look through this, think about all the different things that you're going to need to talk about. And when you're explaining loudspeakers for me, start with an AC signal, then talk about this apparatus of solenoid or coil and magnet, and then explain the sound wave and where that comes from. So here we go. An alternating current signal is put through the coil. Mark, actually, because they haven't told us that, have they? Currents have magnetic fields around them. These magnetic fields interact with the magnetic field of the permanent magnet. Mark. So this, somebody asked for the motor effect. This is an example of the motor effect. This means there's a force on the coil. See, motor effects making a force from a current and a magnetic field making a force. As the current alternates, the direction of the magnetic field, and so the force changes too. Mark. So basically the force is also now alternating, and this makes the cone vibrate. And as it vibrates, it causes high pressure compressions in the air and low pressure rarefactions. And this is the sound wave. Okay, and then the last bit of extra detail I've put in here is that the sound wave has the same frequency as the AC signal which produced it. Now we do mark these on a level scale, okay, so we don't just decide how many marks they're worth, okay, although that's kind of how I've shown you to mark it there. But essentially the difference between a kind of 5 or a 6 is how detailed and how well linked the things are going to be. So at level 2 might make some relevant points, but not really very precisely, and there's not very well kind of linked together. But a level 3 response will have thought through the kind of logical sequence. Okay, it's very important. And so I think I get the last mark, and hopefully you can understand this starts from the alternating current and ends with the sound wave and links back to the actual alternating current that produced it, and that is a good response. Difficult thing to do. You're not going to do it no matter how bright you are if you don't stop and plan before you write something down. Take my advice. Okay, I'm just going to be back in just 2 more minutes. Okay. excuse me, I'm just going to do the last one and then I'm going to say good night. I'm not going to say good luck because you're prepared for this and you're ready. Okay, I hope this has been really useful for you. So figure 20 shows a piece of apparatus called a current balance. Okay, when the switch is closed, the part of the wire labelled X experiences a force. So this is the diagram, and experience a force due to the motor effect, which somebody was asking for. What's the name of the effect that causes wire X to move downwards? That's the motor effect. Suggest one change you could do to make the apparatus in figure 20 that would increase the size of the force that wire X experiences. So there's two things you could do. You can increase the strength of the magnet, or you can increase the size of the current. Now, don't say a bigger magnet, because that is what a lot of people will say. Okay, it's about the strength of the magnet. One of those two is fine. And this last question is one of the really tricky calculations where you have to think about doing a two-step calculation. So there are two equations or two principles you have to apply to get this mark, to get all of these 6 marks. Okay, this is 6 mark calculations. New for you, new for this year. So wire X is 5 centimeters long and carries a current of 1.5 amps. So that is 5 centimeters long, like in the magnetic field. A small weight causes a clockwise moment, there's a clue, of 4.8 times 10 to the minus 4 Newton meters. Calculate the magnetic flux density where the wire X is positioned. So you need to get something, an equation to calculate the magnetic flux density. And there's only one equation that's got that in at GCSE, and that's force is magnetic flux density times current times length. So I could probably do this, right? Now I encourage you, if all you think about is that, and you can put down some relevant numbers like the current, 1.5, and the length, 0.05, which is into meters, so let's convert these into meters, why not? Okay, then you're going to get at least some of the way there, and you're going to show us that you can do some of the things. So write down the equation, sub the numbers in, pick up a few marks. Now the point was that it's balanced, and they've given you the clue at this moment, so that you have to start with the principle of moments, which is that the sum of the anti-clockwise moments is equal to the sum of the clockwise moments. So that's where we start. We've been told one moment, and we know a moment is a force times a distance, so here's where we use this distance here, 0.08 meters, or 8 times 10 to the minus 2. Into the calculator, and I said I'd show you how to use the times 10 to the button if you don't know already. Then to get this answer, you do 4.8 times 10 to the minus 4 divided by 8 times 10 to the minus 2. So on the calculator screen it reads off the entire sum that you're going to do, equals. And you want to press the D button, obviously, decimals, and you get 6 times 10 to the 3 newtons. Sorry, 6 times 10 to the minus 3 newtons. And now we've probably got 2 marks for getting some of the way through the calculation. So always think, can I pick up a few marks for getting part of the way through? Now this is the force that I'm going to put into F equals BIL to work out B. So we've selected this equation and rearranged it, and that gets us a mark as well. And then inputting this number with the current 1.5, and we want amps and anything else, times 5 times 10 to the minus 2. Now be careful, because they've given you 2 lengths, and you need in this equation to use the length in the field, which is this length. So put all those numbers into the calculator, you get 0.08, which is absolutely fine for the, well, numbers in would be fourth, and the final answer 0.08, or 8 times 10 to the minus 2, which is the same number, 5 marks, and 1 mark for knowing the unit of magnetic field strength was Tesla. So actually, even if you haven't done anything else, you get 1 mark for knowing that the unit of the answer, because it asked you to calculate magnetic field strength, was Tesla. Righto, I'm just going to have a real quick look at the chat. I don't have any more time for you guys now, I'm really sorry about that, but I have done about an hour now, so that's going to be there. I do combined, there's links in the description for combined science as well. What I suggest you guys do is you just spend maybe another half an hour looking through a few little areas ready for the thing tomorrow. If you do OCR Gateway, then there are links for lots of questions on that down in the description as well. And there are little playlists for different sections on my channel as well. But then get yourself to bed nice and early, have a relax before that bed so you sleep well, and you go in there and just show it your best. Okay, I'll look forward to seeing you on results day. Okay, I'm going to do a little live feed and open my results live on results day, okay, my own GCSE results, right? And I'd just love to hear how you guys do. I'd also love to hear tomorrow, happy birthday, and I'd love to hear how you're actually doing. So I'll pop up and do a little live feed at some point and just ask you how it went, and you can let me know how it went. After tomorrow, make sure you just go ahead and enjoy your summer. Okay, I'll just let this thing play you out.